Uh, I want to introduce you to our first tutor, Stefana Janicijevic. Stefana is a researcher and PhD at the Faculty of Computer and Information Science, University of Ljubljana, and she will hold a graph-based approach to text mining solutions. Enjoy.
Thank you very much, colleague. I wanted to say I'm honored to participate in Data Science Conference this year. Especially glad because this year is the 10th of anniversary of this conference. So it's very great pleasure to be here with you. And I would like to greet you all and wish you successful acquisition of knowledge, sharing of knowledge, and networking. So since Luca introduced me, I will share my screen, the whole screen. I hope you can see. So what is the concept today? We will speak about graph-based approach to text mining solutions. It's let's say basic intermediary level of presentation, since graph theory is a very huge field of research and with very much advantages in itself. And what I have to say, we have alternation between graph approach, graph approach presentation and graph approach coding in Visual Studio Code. So I will switch between presentation and coding, since I want to explain some theoretical concepts and to switch on practical examples. And also probably I realized that I have many procedures that I developed in Python. So probably I will not typing because it's too much time. We don't have so much time. So I will show you and run code with you, and we will talk about it. Let me introduce the content. Introduction, short overview, dataset, graphs, knowledge graphs, some theoretical part that we will go through it now, and practices, or let's say Visual Studio practical part. So considering introduction, we are starting from text mining as a general approach, one of the core topics in machine learning. It extracts key information such as entities, concepts, relationships from raw data, transforming unstructured text into structured data. What is second, let's say, ground truth or basic concept? It is knowledge graph. Knowledge graphs organize data, connecting entities and relationships to form a network that reveals context and connections, enhancing reasoning capabilities. Third concept that is also very important in the text mining field is large language models, which you can see leverage structured networks to provide context-aware processing. And we also have enabling advanced application like sentiment analysis, context-rich recommendation, and accurate question answering. Together, these, let's say, three pillars, as I can say like this, text mining, knowledge graphs, and LLM, create a sort of cycle of data transformation and makes AI systems more insightful, reliable, capable of sophisticated understanding and decision making. So we will present in this tutorial small text mining process using graph-based approach, and data source will be textual file presenting sample of collocations in Slovenian language. So short overview about some practical, let's say, concepts. So we will create a graph. We will use Network X mostly, some also other libraries, centrality measures as a traditional approach in graph theory. We will also calculate shortest path analysis, node embeddings, do clustering, visualization, and do some, let's say, more advanced algorithms that I did not put on this slide. Considering data set, I mentioned it is a Slovenian data set. I mean, I'm working at the Laboratory of Cognitive Modeling and Machine Learning at Faculty of Computer Science, University of Ljubljana in Slovenia. And we are dealing with my particular subfield is text. We are dealing with also many other AI systems, but my personally is text mining. So I'm responsible for data engineering, for data preparation, and for AI ML modeling in text mining sources or databases or whatever. So we have several level of data sources. So I just took, let's say, and extract very small sample. We have millions, hundreds of millions of data. But I found one, let's say, what would be interesting, found one table with collocations and do sample from this corpus of Slovenian language collocation table. Collocations are any part of sentence and expressions. And I I merged them with some other sources that present senses of sentences and text and paragraphs and collocations. So we have senses of, so we are trying to find senses and more senses, multiple senses on every part of speech, let's say like this, or POS. So I really simplify it for us today because it's a huge field and we can really do a lot of transformation and a lot of representation of this. I took one table you can see here. So joint representative form is a column that represents collocations, everything in Slovenian language, and it's not readable like you can see because of encoding here, but it's readable, it's not a problem when we are dealing with it. Indicator is sense. And keyword is also relationship between sense and collocations. So we have collocation as a starting point. We have some keyword from it. Evropski supermarket. Keyword is supermarket. And veća trgovina, or let's say huge shop market, let's say like this, is explanation of this Evropski supermarket. But you can also see that we did similar senses for different part of speech. So according to keywords. So it's something we will, let's say, we can let's say apply more advanced algorithms to find more sense as I started with that. So we have one sense for collocation, but we can find more senses. Some of these, let's say, insights and research are ongoing process. So we will just go from the beginning how we did something. So we start with the graphs. Graph theory, mathematical concept. It's a part of combinatorial optimization of mathematics. It represents, so graph represents mathematical structure used to model pairwise relationship between objects. There are several formal definitions. I mean, one maybe more simple or simpler definition is when you have ordered pair of vertices and edges. I gave you here triple order, like vertices, set of edges, and function in the incidence function that associate each edge of unordered pair of vertices of G. So sometimes I'm calling, so nomenclatura such as nodes or vertices are the same. So sometimes I'm saying nodes, sometimes vertices, it is equal. Also edges, you can have edges, relationships, links. So these are also the equal nomenclatura. Graph consists from a set of vertices or nodes and edges, connections, where vertices represent entities or objects and edges represent relationships or connection between vertices. You have many types of graphs. Let's say some general, very high level, undirected and directed, unweighted, weighted. We also have simple, multigraph, connected graph, complete, planar, cycle, tree, so many other. Applications are very wide: social network analytics, computer network, biological network, telecommunication network. So everything where you can find some relations. I will also highlight GNN as a new, so this up to now, it was traditional approach, traditional explanation of mathematical graph theory. Let's say last 20 years, we are working with neural networks, and we are trying to enhance to adjust mathematical concept to neural networks. So also graph found its place there. So newly concept of graph theory is a graph representation with characteristics such as a learning representation. So this is new. So we found that every node, it could be anything, so not just node, but let's say node, edges, or entire graph could be some kind of vector embedding. And it could represent learning, a representation from where you will find patterns. According to that, you can find prediction of everything, what you are searching for. So this, if I will talk about, I mean, when I'm talking about node embeddings today, I mean, when I'm talking about embeddings, I will talk about node embeddings. So we will not go far away today so much. Also some key mathematical topics, what is interesting, what is important to understand, linear algebra, geometry also, analytic geometry, they have just very strong connection between each other. Incidence, adjacency matrix, eigenvectors, eigenvalues, vectors, matrix multiplications, and K-neighborhood. You can find that some other like matrices and vectors. Also, linear algebra is something which exists in all machine learning algorithms, less or more or less, like as you like. But K-neighborhood is something which is concept from the graph. So this is really originated in the graph. So today you can say you can see, and you can talk about it also, about many algorithms that use neighborhood of its structure, but general original concept and generality, let's say abstraction, comes from the graph theory about neighborhood, because just node as an object could have connections with other nodes. And we are using that concept in other machine learning because it's very useful. We will also, we will highlight today knowledge graph as a topic, structure which represent information about entities like people, places, concepts, and their relationships. Knowledge graphs, let's say, it connects data points into a graph of nodes and edges. Knowledge graphs emerge to solve the problem of organizing large, complex information in ways that humans and machine can understand. They bridge gaps in data interpretation and enabling better insights from data connection. Also, applications like NLP and the recommendation system, these are very important resources in knowledge graph, let's say like this. A knowledge graph helps AI system to identify and link entities in data. When dealing with names, locations, or organizations, for instance, a knowledge graph can verify and connect these to structured database. I can say what I highlighted here. You can see bold text. The relationship between these entities capture the context and meaning of how they are connected. So this is the most important insight from the knowledge graph. Okay, we will go now to code. We will return to see so what we get, let's say like this, what we obtain. So as I mentioned, I didn't put all this for, I mean, typing now, because I will waste my time so much. So it's better like now to run this. And so I hope that you have a requirement list with libraries that we will use. I'm using Visual Studio Code. You can also use whatever you like, Colab, PyCharm. And I will go really with very simple approach. So as I mentioned you, I'm using merge all. You saw that table. Usually I'm doing some kind of when I'm prepare some data, I'm preparing sometimes in Orama, Python, I'm preparing in SQL, in pure Python, whatever, sometimes in R. But the thing is when you prepare data, you want to see a little bit how it is behaving in your code script. So firstly, very simple, list all columns. I can see my columns. I knew them, but these are these columns. Also, yeah, I will also prepare some kind of smaller table because I don't want, in this particular case, all columns. I don't want to investigate this table. Also very simple Python. You can see pandas functions. It could be done on many different ways, but for this example, I want to see immediately what I have. Okay, shaping is giving the size of our data. So I expect about 1,700 approximate records and 3 columns. That is important for me. And I want to see them a little bit, if you agree with that. So it's better than in this, let's say, form and encoding, because I can see all these letters. And it's more clear what I want to obtain. We are going further. Okay, now we are coming to prepare more structures. So what is the thing? You can have you can prepare any approach on several ways. Let's say like this. And when we are dealing with some approach, for example, some just graph, I want to know what kind of data structure is most important and most valuable for me. You can do pandas on everything. You can do, I don't know, list data frames, dictionaries, everything. You can do JSONs, of course, XML libraries, and prepare XML data. But tuple of data is something which is more convenient for the graph representations. So it's a way of iteration over rows of a data frame. So I'm using data frame here that I prepared upstairs, and using iter tuples function because it's returning each row as a tuple. So we prepared at the end a list of tuples because I'm putting all that structure in a list. So you'll have a list of tuples. So this is one tuple, and every tuple present me part of graph structure. Okay. And this, okay, I will also leave your comments here because I also prepared that with comments. And creating graph. Graph can also be created on a several way. I'm using, there are many also libraries on GitHub you will see for knowledge graph and everything, but these libraries could be more advanced for approaching, because you need to have some dependency installations which are more complex than this. So I decided for our presentation today to use NetworkX, and I do also iter rows. So I'm keeping every row from the data frame, looping through each row in the for merged, and ignore the row index. Use only data that I get from my record in data frame. Also, this is very nice code snippet for data visualization, graph visualization. What we see here, we have, I will run it because you will see that some part of code will run several, maybe more seconds or even several minutes. We have part which present node embedding, so it's about 10 minutes it will run. So I will just run it and explain Spring layout. This is a layout function that position, let's say, nodes with a force-directed algorithm. What is also interesting about parameters, we have G, seed, and K. Seed probably you know for, let's say, controlling mechanism of reproducibility. K, this controls the spacing between nodes, so higher values will push nodes further apart. You can also experiment with this. And G is graph, is it like this. So we can also say about other functions like is draw and draw network X edge labels. We also have alpha, controls transparency. We can have full transparency or opaque, or I mean, a full opaque or full transparent, something like this. Also other functions, network 6 edge labels, draw labels on the edges. Yeah, and great that we finish explanation, we get visualization. Of course, if you are doing in some kind of production, you will not do this like for, I don't know, 1 minute or 2-3 minutes. And this is not the way of working for really big data. So in that case, you are not working on CPU, you have GPU and everything. Very long story about DevOps preparation for graphs and DevOps configuration for implementation of graph algorithms. So it's a topic for itself, but just to be aware that usual local computer with CPU, for example, which I have here on this machine, is not for bigger than 2,000, 3,000, 4,000 maybe, but after that it's useless really. What else? Yeah, I have very simple investigation how much nodes and edges they have, and I expect 2,400 and edges 1,700. I don't know if you if you notice here. So when we are preparing graph, we are adding edges from the merged, and we are adding nodes from the merged, but in a way that head and tails are nodes and row is relation. You remember that we rename here, so we have, so this is node, and this is relation. So we have 2 columns for nodes. We didn't do it for 1 column, we did for 2. So we we did collocation. I mean, in our language of Slovenian language, let's say like this database, we have collocation, which is head node. We have indicator or sense, which is tail node. We have keyword, which is relation. So I hope it is totally clear. And that's why we have we have bigger number here. It's not just the shape you saw 1,700. It's not just this, because we also have nodes in other. So we are counting the both, distinct, of course. And we have a relation, relation between edges and nodes. Great. Now we came to centrality measures. Great. So degree. Degree is very important centrality measure. I will just delete this and I will run it and explain. So when you are dealing with degree, it's also part of traditional graph approach. We want to calculate and to count a number of direct connections or edges that each node has. From one node, so from each node to all other nodes. So this is degree centrality, number of edges, number of relations. Nodes with higher degree, logically, are more connected, let's say like this. And we can count how much. You can see, so I didn't do preparation to have some fancy data, I mean some ideal distribution, to have some, I don't know, nodes that are ideally distributed, such as that you have nice numbers, I mean, inside, to have some highly connected, weakly connected, or something like this. So I took sample as it is. It is something that would really change if I put all population, and it would be much, much higher. But this is, we can say sparse, because we don't have so much connected in this kind of data. It is different in different kind of data. So you can see for every collocation or every node, not just collocation, every node, what is the centrality. And usually it is the same, because many of them just have one or eventually two or something like this. If you want to sort, to find what would be most interesting, I mean, to find for every node how much, and extract what is the best, I mean, the degree in our graph. We will also type this. We will see chemistry element, collocation, plot with this degree, sport, drevo, želja po uspehu. If we are, yeah, it's chemical element in English, plot like yield, fruit, sport, drevo is tree, wish for success. So they have some, let's say, advanced or higher degree centrality than others. So you can see here what I used. I used degree centrality function. I'm calling graph in it, calculate degree centrality. I'm iterating over and creating a list of tuples, let's say like this. I'm iterating over that object and through all items. I store everything in a degree list. I'm using lambda function here, which is anonymous function. Yeah, because I want to sort everything from that list, and x of 1 is accessing of the second element in each tuple. So it's a way for degree centrality. If we want to calculate the number of components, so one of the interesting insight. So we expect 671 components inside. Also, this is the function number connected components with graph G in it. Same manner, I will, let's say, repeat with betweenness and with closeness. So this is betweenness. I will also run it and explain. Okay. Betweenness is based on how often it appears on the shortest path between node and other nodes. So you are calculating shortest path. Node with high betweenness for every node. Node for high betweenness, centrality can act as a bridge between different parts of the graph. You also have some results here, but if you like to have to sort and to have inside maybe in a way to see the best betweenness, the story is very similar to degree. So these are all traditional measurements. So again, list of betweenness as an object where we store all betweenness centrality items. We are using betweenness centrality function, going through all items and store node and centrality. So for every node, its centrality is calculated. Also, we are sorting and printing, presenting the best. And again, you can see chemistry element. But with betweenness, I mean, I know it's just on 2 decimals. If I put maybe 10 decimals, you can see betweenness that have some values that are slightly more than others, but it's very let's say weak, because this data set, which is not, I repeat, prepared as an ideal data set with a distribution of nodes, great to see everything. What is here also interesting to present? You can see largest let's say component. So largest connected component. It's create a subgraph from G containing only the node in largest component. So these are subgraphs in a whole graph. We are computing the betweenness centrality for each node, and also we use normalization, because betweenness could have really unstable scale, let's say like this. I mean, not unstable, but huge scale. So we have to normalize according to other. So we want to compute the betweenness for each node in the largest component, because we didn't find in this way really betweenness that is valuable for us. I mean, it's too small. So we wanted to separate the graph on subgraphs, to calculate betweenness for each separate subgraph, and to normalize the values, as we can understand which node in these components are really significant. So this is our core and our goal to find. Yeah, I can run it. And again, you can see chemistry element, as I mentioned. Now you can see the betweenness is higher. Napad chlorum, dozvolj kalija, fluor, pastes fluorum. So these are in English chemical element, attack with chlor, kali, big K periodic system. I hope that we can say kali in English, I'm not sure. And fluor, big F. So we are calculating, they are also 0 here. But the thing is that chemistry element is something which is more significant than others. What can I say also here? Items, for example, returns iterable view of the dictionary that we have here, and we are producing tuples at the end. So again, dealing with some data structure, remember please tuples and items, a neighborhood. These are very important structures for, and subgraphs also for when we are talking about graph theory in computation world. Okay. I also have here significant betweenness, also much more that we didn't see here, because I typed just 10. So significant with betweenness. Also, you can see it's so small, but it's okay. I mean, this could be really significant with centrality greater than 10 on -5. So this is dictionary structure. Let's say like this. Create a dictionary that only include nodes with a centrality value greater than 10 on minus 5. So 5 zeros 1. Okay, closeness centrality is our last centrality measure. And last part, maybe, I mean, it's not, we will also have some other measurement about traditional approach. So closeness centrality, again, measures how quickly a node can reach other nodes in the graph. So these three measures, also page rank is something very important, but I didn't calculate that. So degree centrality, betweenness centrality, closeness centrality, totally are speaking about graph graph elements behavior. So closeness measures how quickly a node can reach all other nodes in the graph. And we are calculated it through the inverse of the average shortest path distance from the node to all other nodes. So we want to find from each node shortest path, to find average shortest path for each node, and to find inverse of that. Again, some linear algebra transformation. Nodes with higher closeness centrality are considered more central. They can communicate with other nodes more efficiently. And if we want, yeah, this. If we want to sort and to find the best in closeness, about closeness centrality, I mean, again, chemistry elements, sport, plot, I mean, chemical elements, sport, yield, tree are probably higher and more significant. Yeah, at the end, we have visualization of all three centrality together. It's very nice picture. So I will run for you here. You can see the functions are pretty same like we had upstairs. Annex dotted row and subplot and something like this. So we will not comment so much about these functions. We will go further because it will run. So what is further? Further is, yeah, to see our conclusion about centrality measures. Most values are measured around 0 to 0.02, indicates a sparsely connected network where few nodes have significant number of connections. Nodes with higher degree centrality are relatively more connected compared to others, even if the absolute number of connections isn't very high. Betweenness. This is interesting to understand, to be understood. Largest connected component, let's say, give us insight that the first output showed that chemistry element has the highest betweenness centrality of 1 within the largest connected component. This means that it plays a crucial role in bridging different parts of these components. While many other nodes in the same component have 0 betweenness and indicating they aren't positioned on any shortest path between other nodes. Drevo and v kulinarki and angliški jezik. I also remember sport, but I didn't put it here. And yield and želja ka uspehu or wishing to success. But also, yeah, they have significant betweenness, but less than chemical element. Closeness, again, chemistry element. This node has the highest closeness centrality in the results. It can reach other nodes in the graph more quickly than the others, making it potentially influential or pivotal node in network. Again, sport, plot, drevo. Nodes have a lower closeness, suggesting that they are relatively more distant from other nodes in the network. If we let's say drop off, if we indicate a significant drop off of chemistry element, and this could suggest that while most nodes are somehow isolated, chemistry stands out as a more interconnected to accessible node. So this is our, let's say, conclusion about centrality measures. Now, our next practice is sense solution. Sense solution is, let's say, one practice or one example that is created according to relationship between collocations and keywords. We want to find most relevant sense for the new collocation. So we don't have this collocation that I will give you. The aim and the goal is to predict what would be the existing sense from our set of senses according to the new collocation and new keyword. Similarity is based on centrality measure, and I used degree centrality. I could use also betweenness or closeness, but I did this as a simple approach and basic approach just to introduce how it can be done. Also, centrality measures are not good enough in a really productive environment. I mean, in a really, if you're really looking for some, let's say, advanced results, you must use semantic approaches. So not these traditional approaches such as betweenness, closeness, and degree, because we are missing semantic approaches here. And what is the best way to have this kind of semantic approach? GNN or node embeddings. So, but this is some other topic. Now we are dealing with traditional degree centrality. So we assume that the new collocation is semantically similar to the existing senses. So that is our assumption. And we have to calculate centrality measures to identify relevant sense. Oh yeah, you can see we have our figure now with the degree between the centrality together. Let's say like this. Okay, yeah. So this is my procedure. All these procedures could be done. I mentioned maybe I didn't go into the details, but I mentioned that I did this pretty simple. I mean, this kind of design of our script, because I didn't want to complicate with functional programming, with object-oriented programming, but since this is example, this presentation, and we want to see some results, but if we are dealing in some productive environment, if we are dealing here with, let's say, real data, really big population, this usually could be just a part of some huge functions or some huge objects that we have to install and implement through as a backend software engineers and or as a ML engineers and big data engineers. So this is really just part of one big structure that is also very, very advanced to be prepared. So we have degree centrality. I calculated again. We have closest tail. Tail, we said it is sense, it's indicator or sense. And we have maximum similarity. So we want to find new collocation voda, which is not existing here. You can also check just pure voda. I mean, it's, you know, you have bamboo voda, you have this wheat water. I mean, it's water, but pure water there is no. We have assumption that it could be similar. We also add keyword vodonic. There is no vodonic. Here vodonic is H in a periodic system of elements. So you are giving new let's say, new record without, and you want to find sense for it. Okay. Yeah, it is done because, yeah, I see it. Yeah. So what I did did here. So technically, I use for loop. I loop through all nodes. I ask if nodes have connections. I'm using get method. Get method is used to retrieve the value which is associated to with a specific node key. If node is not found in the degree, it will return 0 instead of anything. And when we have that relevant tail, we will just, if the closest tail, when we find the closest tail, we want to visualize and to find new collocation with a new keyword has some existing relation. So now it's running because we are also drawing this. We have figure, I mean, we have chart. But you can see voda and vodonic is connected to chemistry element. But I must say, this is according to that I know that chemistry element has highest degree and most valuable and most significant. And if and in that case, I try to find what else could be connected with that. So I really typed here intentionally voda and vodonic. If I typed, if I wanted to find for, I don't know, supermarket, it would be error because again, it would be related with the chemistry element since I'm looking connection according to degree centrality. So the most important is how you are looking the connection. That's why I'm told you, if you are dealing with a real productive data, I mean data, you are dealing with some project in production, in real environment, you have to take into account also these traditional measures, but also some other measures because like embedding measures, because semantically we want to find semantical connections, not just traditional calculations that we have here. Yeah, you can't see now here because but they are inside. You can see here new collocation voda connected to chemistry element with relation vodonic. And that is something which is calculated here. So this is very nice approach, very nice idea. How would you do so this sort of predictive analytics? This is tool of predictive analytics. So you are finding new text with existing connections. That is the thing. Next practice, shortest path analysis, and I hope, yeah, that this shortest path, yeah, is the last from the traditional, let's say, field of graph theory. So I started with let's say, historical research, and after that, I'm coming to the new approaches at the end. But this traditional shortest path, it's very interesting for me. Focuses on finding the shortest path between two nodes, two collocations in the graph. This can help understand the connectivity between different entities and the minimum number of relationships required to connect them. So we want to have, we want to find the list of nodes that represent the shortest path between two nodes in a graph. And we want to create a list of edges at the end that connect each consecutive pair of nodes in a shortest path. Yeah, shortest path analysis. I will copy it. It's easy for me to copy again and to run than to just show you. I mean, I think it's better. So yeah, I also took two nodes. I can took nodes from the list of tails, from the list of heads. I took from the list of heads element oblique. You can find here. Yeah, this is element oblique. Zaimanje oblique. Oblique in English is C, ugljenik. In Serbian, oblique Slovenian, and C in chain periodic element chemical. So you have two nodes, two collocations. So these are part of speech when we are talking about it. What we are doing, find the shortest path between two nodes here. Generate, I will also start it because maybe, yeah, it will run as well as I'm talking, so great. So find the shortest path between two nodes. We are storing in shortest path variable. We are using shortest path function with very simple, you can see parameters of the function, G, source, and target node. We want to generate node position using Spring layout because I will draw for you at the end. We do visualization. I will also use here list comprehension that iterates through indices of shortest path, except for the last one. So that's why we have -1 here. And at the end, yeah, I see some questions here, but I don't know. Maybe better to finish some part of, and after that we can talk. So we also here create a tuple of representing edges, let's say, between two consecutive nodes. Shortest path from E and shortest path from E plus 1. This is part tuple of representing edges. As a result, we have path edges at the end here, and it's a list of tuples, each representing an edge in the shortest path. We will draw everything, highlight the shortest path with red, let's say, line like this, and make output, yeah, and we can see. So this is something which will be more comfortable if I will have really small data, but in that case, I tried with a smaller data, but in that case, it's not very, yeah, because I cannot calculate other things. This is something which, yeah, you can see, and you can also practice this procedure on your data maybe. But the thing is that that is very, very interesting. So you can find a list of shortest paths and to find the best shortest path from here. And you can see here, element oblique and zaimanje oblique are connected. I have the path over chemical element. So element C with taking of C are having connection over chemical element node. So we remember that we have that as a node. So this is very also interesting, let's say, insight from our data. And now we are going to the node embedding, and I must maybe hurry because I have a more advanced results. So node embedding, what can I say? Node2vec is a popular algorithm you can see here for generating vector representations or embeddings of nodes in a graph. We are capturing relationships and structure. We are combining principle from random walk and word2vec famous library. And we are using main parameters such as P as a returning parameter and Q in-out parameter. We are controlling the balance between the searching with the breadth first search and depth first search, famous strategies for searching over graph in a wideness, in a deepness. By adjusting these parameters, we have Node2Vec to explore node neighborhoods in a ways that capture different structural patterns, allowing for flexible and expressive representations. These embeddings can be used in downstream tasks such as node classification, link prediction, community detection, enhancing the predictive power of machine learning model by incorporating relational and structural information from the graph. So we will prepare from our traditional graph, from our traditional vertices or nodes, node embeddings from them. So we will have vectors as a nodes, not just strings or whatever. And we will apply it for the clustering. That's why I will also present here clustering, famous method in text mining, maybe one of the first. So how we can group and cluster our texts and part of speeches and characters and everything. So whatever. In our case, we are dealing with collocations as a part of speech. So how we can cluster our collocation together and our, which is more important, our senses of the collocation. So if we can cluster senses, we can very easily assign new indicators to the cluster collocations. We are performing k-means clustering on node embeddings. We do k-means clustering visualization, perform the Basquiat clustering on node embeddings, and the Basquiat clustering visualization. Yeah, this is other. So we are jumping to our next practice, and it is node embedding. We can do part by part. So we explain what is node embedding. This part will be longer than any other, but we will go and explain. Our aim, our goal is to generate, reduce, and visualize node embeddings. Node2Vec generates embeddings or vector representations for nodes in the graph. These embeddings capture structural and neighborhood similarity. So you can see neighborhood similarity here, allowing nodes with small, similar rows and connections to have similar embeddings. We have G as a starting point, the graph on which Node2Vec will be applied. We have some parameters here. We will explain dimensions 46, size of each node's embedding vector. It's also a very famous concept that when we have node embeddings, we have to set up the dimensions of that. I will not go into other large language model embeddings, which are much higher, much more complex, but okay, we can also have it here if I have population of several millions of nodes. But now with this, 46 is pretty good. Walk length is equal to 30, the length of each random walk starting from a node. Walk is a sequence of nodes that helps Node2Vec learn about the neighborhood structure. So walk length is very important. And the number of walks, 200, number of walks present to how we perform for each node. And with number of walks, we are capturing more local and global relationships. Workers is something with CPU cores. Let's say we will skip that. Windows equal 10, maximum distance between nodes in a walk considered as a context for each other, similar to the context window in NLP. Minimum count equals 1, ensures even infrequent nodes are embedded. Batch words equal 4, controls the batch size for training. Yeah, and what is interesting, you can really here understand how much will you play with the parameters. I will also give you here this visualization. What else? We can adjust these parameters, I told that. We training model with this notvec dot fit. I mean, here is training the model. And in embeddings, we are getting arrays for all embeddings for all nodes in this kind of instruction. What we are also use, you can see TSNE. That is why is also very slow, because we are drawing all these embeddings, but we cannot draw really in some particular usual time if we draw all dimensions. So we want to reduce dimensionality using TSNE or PCA, whatever. TSNE reduces the high dimensional embeddings to 2D space, making them easier to visualize. We have two components. The number of the number of dimensions for the output is 2. Perplexity is 10. It controls the balance between local and global relationships in the data. You also can play with that to adjust these parameters. This affects how TSNE spreads out the nodes. If we have 400 iteration, we will see the number iteration for optimization. Higher values allow better convergence, but increase processing time. Our result is like we have embeddings 2D in a 2-dimensional space. It is 2D array of shape. What I can say, about TSNE, how it's working. It's one, let's say, probabilistic algorithm. TSNE calculates pairwise similarities between data points in high dimensions, then tries to preserve those relationships in the lower dimensional space. It uses probability distribution, that's why it's probability algorithm, to focus on maintaining local structures. What is local structure here in graph? Close neighbors. So we try to focus on close neighbors rather than global structure to whole graph. In that case, we are making dimensions clearer. With perplexity, we're doing balance attention between local and global aspect. And everything else we said about visualization, you can see here when we finish there. About visualization, you can see that we have x and y coordinates. This is x and y here, coordinates. Of each node, C is blue, color of the points, alpha 0.7, transparency of the points to make them transparent. And we are adding node labels for coordinates with this part of code. And you can see that it's 6 minutes is running and it will run more. So I will not waste my time because we don't have much time and we have some results to show more. We explain k-means that we use k-means and the scan. So now we will going to go to present clustering. I will also run this, so when it's finished, it will be. K-means very famous method. I will not really go inside. It's very old traditional method of grouping similar objects and creating some distinct objects that are each with similar in itself entities. So I adjust here number of cluster with 3 clusters and doing visualization. You will see here visualization. Again, visualization here. Clustering is nice because you can really provide very nice charts. here and here. We are using for clustering embedding 2D. So we are not using embedding 46 dimensions. We are using embedding 2D, and we are visualize x and y coordinates in 2D space. And what is else interesting here? We have CMap, for example. CMap, yeah, a specific color map to use for coloring the clusters. And we have embedding plot, show how similar nodes are in the terms of embeddings, which captures the similarity-based relationship. Yeah, that is. And while we are waiting, yeah, node embeddings several minutes more. After this is the longest, so after that it will be faster. When we complete KVs, I can say that we are going to the DB scan. Why DB scan? Yeah, I left you here. DB scan can find, I left you explanation. DB scan can find clusters or arbitrary shapes and sizes, unlike k-means, which assumes spherical clusters. DB scan is also robust to noise and outliers, since they are not assigned to any cluster. I didn't do noise data preprocessing or outliers transformation. I didn't do that. I know that, yeah, it's very common practice, but I didn't want to do that because I wanted really to do this on our raw data, but sample from a very small sample from our Corpus Slovenian database. What is also interesting to say about the scan? The scan clustering group is, let's say, groups points based on density. So it's grouping points based on density, making suitable for data with irregular shapes and noise. You can see parameters such as G, seed, and K, very similar. K controlling the spacing between nodes. Higher values spread nodes further. Epsilon also you can see in a model. Maximum distance between points to be considered as a neighbors. The minimum samples equal to the minimum number of neighboring points required to form a core point. Core point, when I'm saying core point, I'm saying about target point in every sphere of density cluster. If a point has fewer than minimum samples neighbors, it's classified as noise. And we are returning cluster labels. We are returning array assigning to each node like this, and each label to each node. And this is very, as I said, robust to outliers and classify. It's good classifier for noisy data. Let's say like this. Okay. Visualization of cluster is here. Yeah, it's a long process, what to say. That's why traditional methods on smaller data are, or some other way of running. When we are, let's see, just a moment. No. Yeah. Embeddings are finished. Visualization of embeddings are finished. So we can see node embeddings in visualization here. In 2D spaces, as we said. And also we can see k-means clustering in embedding space with node labels. And we can also see k-means on this way, let's say, It's better visualization than upstairs. And now performing DB scan, which is far more better. And far more clustering will be far more better clustering than k-means. Okay, as long as we are waiting DB scan to be finished, just to see here, yeah. So we are waiting DB scan. We are jumping further on our knowledge base graph. Now we are coming at the final. We have about 20 minutes, so we are at the final. Let's say the maybe advanced results that we have here. We will initialize dgraph now. So we will not go with our graph, we will do dgraph. In dgraph also we will use tuple of data that we prepared at the beginning, you remember probably. And after that we will present, let's say, 3 algorithms. First algorithm, everything from first, second, and third. First is the biggest one. This is a presentation of S-graph embedding. This algorithm generates semantic embeddings for collocation based on the importance of connected indicators. We also we are using removing, let's say, method for removing of an indicator with the least weight. So we are removing indicator with least weight. Also, we randomly remove that indicator based on some criteria, let's say frequency. And we are creating embedding based on the refined, we call it con prime set. So some refined set you will see. We have 2 types of algorithms, basic algorithm and improved, fine-tuned, or let's say, I don't like to say fine-tuned, I like to say improved algorithm because it's not really fine-tuned, it's improved with additional methods. Algorithm 1, scientific papers are focusing on semantic graph embedding and text mining. Algorithms for graph embedding usually involve more sophisticated techniques such as random walks. So I will say random walks, matrix factorization, attention mechanism, and graph convolutional network. These 4 are, let's say, pillars for this kind of semantic recognition. Random walk method like deep walk or NoToWalk, which use random walks on the graph to generate node sequences, which are then used as a learn embeddings. Matrix factorization techniques such as graph factorization and use matrix factorization or decomposition. I hope that we all remember what is matrix factorization, and we are dealing with adjacency matrix or similarity matrix. Attention mechanism, it's a recent approach, novel approach, let's say like this, involve graph attention networks, which use attention mechanism to weight the importance of neighboring nodes. So this attention mechanism is very important today in transformers. We have them in LLM also. Graph convolutional networks, these are convolutional operations over the graph structure, and it is using to learn embedding. I will go through all explanation about algorithm 1, at least one, and because it's useless to just show code without explanation. So we are modifying one algorithm from the state-of-the-art paper to better reflect stable graph embedding techniques by using the following steps. We did weight-based node pruning. Also, procedure from graph theory, pruning, very famous procedure. Random walks for contextual embeddings, dimensionality reduction, iterative refinement using node importance. About weight-based node pruning, instead of randomly popping connected nodes, we can use connected weights to determine which nodes should be kept or removed. We could use threshold, or we are using threshold on the weight or other criteria, and keep important connections according to that criteria. According to second random walks for contextual embeddings, we incorporate random walks to generate sequence of nodes similar to NLP techniques used in the word embeddings. This approach treats the graph as a series of sentences and learns embeddings based on these walks. What is about dimensional reduction? It's maybe the highly known to many practitioners from data science and machine learning. After generating initial high dimensional embeddings, we can use dimensionality reduction techniques to project the embeddings into a lower dimensional space while preserving important structural information. According to iterative refinement using node importance, also we are calculating, it's also famous probably for many people, calculating the importance of nodes using metrics such as page rank or centrality can help determine which connections are more significant and should be retained in the embeddings. Our algorithm helps in topic modeling. So it is, let's say, keyword extraction. The code extracts the top keywords from the LDA topic. So we are also apply LDA method, Latin Dirichlet algorithm. We are using embeddings to understand the underlying themes or topics represented in the collocations in part of speech. Topic modeling is performed using LDA, as I said, directly on the collocation data without needing to cluster the embedding first. LDA is generative probabilistic model, again, one probabilistic model, used to discover topics in a collection of documents, and it can work with text data to infer topics based on word co-occurrences. My personal, let's say, digression one, my personal favorite are probabilistic algorithms, so all set of probabilistic algorithms. So one of that Latin Dirichlet of allocation, topic modeling technique used to discover hidden thematic structures in a collocation of documents. There are several procedures which proceed to LDA. So 4, let's say, steps: pre-processing the text, creating dictionary and corpus, definition of the number of topics for the LDA model, and extracting topics. Pre-processing text, we are talking about tokenization, converting the collocation into individual words, which are also field for itself. So dealing with tokenization in all languages are really research field very, very rich. Stop words removal, okay, we know all that. Lemmatization, if applied, it would convert words to their base or root forms, further refining the focus on meaningful terms. What about this? This is all in a let's say group 1 or pre-processing text. Group 2, creating dictionary that maps each unique word to a unique integer ID. This step is essential for transforming the text data into numerical format that algorithm LDA can process. We are generating corpus, which is a list of bag of words representations for each collocation document, where each document is represented as a vector of word count. Group 3, definition of the number of topics. Model analyzes the corpus and discovers patterns of word co-occurrences. It assigns probabilities to word for each topic based on how likely they are to appear together in the same collocation, in the same part of speech. Extracting topics, output of the LDA model gives us the topic as distribution over the words in the vocabulary. So we have at the end vocabulary with the topics. Each topic is represented by a list of words sorted by their importance in the topic. The words in each topic are derived from relevance of the context, frequency of occurrence in combination with other words, and model statistical assignment based on patterns learned from the other part of speech, or let's say shortly from the text, capturing the semantic structure of the data. Yeah, we also mentioned it is probabilistic, involves many stochastic processes, meaning it includes random elements in initialization. Each time when we run the LDA, the initial distribution of topics and words can change. Solution, we want to minimize variability So we can set random seed using the random seed parameter. Also, the number of passes and iteration used during training can affect the model's convergence. More passes can lead to more stable results, but also increase computational time. Solution: experiment with the passes parameters. So please try several higher number and maybe smaller number and make experiment. LDA models, also part of traditional algorithms. They're not novel, let's say, approach, but it's been using all the time. May not converge to the same solution with every run due to their reliance on sampling. If the model hasn't fully converged, it might produce different topic distribution. So we also do evaluation model convergence by inspecting coherence scores. If the scores are low or fluctuating significantly, consider running more iteration or using different initialization. So this is according to my preparation according to algorithm 1. Yeah, we have now, you saw this, we also have dbScan, which is better, and we will go, because we don't have so much time, we will go just to run. In that case, I will just run here. I will not copy. So tuple data, you see tuple data. You remember that we have prepared upstairs from our data frame merged. Here we are preparing dgraph. I also talk to you about dgraph preparation. So now we have head relation tail in a tuple of data. So we have direct connections from head to tail or from tail to head. So this is dgraph. This is different than graph. What is interesting more? Graph embedding. So this is our algorithm. So our function generates embeddings by identifying a subset of connected nodes here, or indicators for each collocation. The function initially identifies all connected indicator, then iteratively reduces the list until it reaches a threshold. Basic parameter is S. Here is our S parameter. This result is an embedding dictionary where each collocation node has a set of connected indicators limited according to the specified criteria. So we have simply reduced list of connected nodes for each collocation in the graph. If I run it, this is the function. If I call it, I have some graph embedding according to my parameter here. If I threshold increase or decrease, I will obtain some other results for that. What is the problem? Problem is that this parameter limit the number of connected nodes according to that parameter. That threshold ratio, our data set is not good for this kind of threshold ratio. We have sparse data sets according to that sparse graph, and this parameter is not dealing well with the sparsing, because sparsing is something which produce very much. We have to really do grid search of the parameters to find the best. So with this, I got solid results. If I put it, I mean, I don't know, 0.1, I will got empty. And many times I will got empty. So, but what I have edges. I want to strengthen my algorithms through edges. I want to use edges more than just nodes, because usually I have two nodes just connected. It's not enough. It's not, there are many sparsing components there. But when I have edges, I can really deal with weights. So I want to have a label of, I mean, not label, but weight for all my edges. And if I have some weight for my edges, I will enhance my algorithm, such as this. And again, I got stable graph embeddings. The thing is, the loop firstly limits the size of a comp prime to a certain threshold based on our iteration. When we speak about embeddings, we speak about collocation and their neighbors and their edges between them. So if we are talking about weights, we want to use, and we are talking about edges, we want to use let's say scaling of that weights and to have calculation according to weight, not just according to number and about frequency of all our neighbors. Leaving some collocations will not have neighbors. I mean, if have at least one neighbor, but with very weak edge, that means that that collocation will not have neighbors. That is the point. So not all weights are the same. So we want to scale our graph, we want to scale our variability, our value of every node according to weights of edges. So some node is more valuable with a smaller frequency of edges than some other, because the weights are targeting higher value. Let's say like this, very simple. So I'm looking now at the time, we are 3 minutes till the end. So I'm thinking what to do, just to run for you. So expected number of collocations are 1,700. We also have length as a function for stable x epsilon. Stable x epsilon is a number of embeddings in the graph according to these parameters that you can also really play with this parameter and see different results. After that, you can see expected number of collocation, total number of collocation processed, and all collocations have connections, for example. But it will be different if I change the weight threshold. So not all will have connections. LDA model here, you can see, so each collocation can be treated as a document in LDA because it's a document. It's algorithm that prepared for documentation processes and processing of documents. We are removing just some stop words. Here, do tokenization, create a dictionary and corpus for LDA, and got some topics here. So I have for every string, for every word in our part of speech, I have value with some kind of coefficients. And if I want to present it in a list, I know that my topic 0 will consist from these several words: nekaj veliko angleščina, del, depresija, besede, demencija, ambicije, vodki, civilisti. Topic second, let's say topic 1, marelec, uporaba, manj, prodaja, tradicija. So this is one algorithm that is more close to semantic approach than to centrality measures that we have upstairs at the beginning. So you can really extract from your data some part of speeches. What else I want to show you here? As you see, we are using embeddings that we prepare upstairs, stable x epsilon. So if you are going through the code, you will see that. Printed the topic keyword as a list, combine all keywords into a set for easy searching, find collocations related to important keywords. So when you run this snippet of code, you will see related collocation based on the LDA keywords are these for example, vrsta čekana, alpinizam je dejavnost, lomak izpred govora. So I have this kind of text, so that is why I'm having this as a result. Total number of related collocation process is 300, approximately 400. I don't know, I am now at the end of the time. I have two more algorithms. So graph description describes collocation based on connected indicators or senses. I mean, you will see that collocation has explanation of what is there. So for every collocation, you have explanation about indicator with graph description. And I'm using graph successor method, which is very useful. Algorithm 3 is graph distance. So I want to measure similarity between two collocation based on shared indicators or shared senses. So you can also find the code here. I hope that you will get our code from today. I will send to our organizers, thanks to them, and also a presentation. I'm not sure now, can Luke also jump in now and say, is it the end, because now it's 11:30.